Thank you for the introduction, and thank you for the organizers for giving me opportunity to talk here. Today, I'm going to talk about 5D1 double perovskites, and in particular from the viewpoint of dynamic Yantera effect. First, I would like to thank my collaborators. Theoretical part is basically with diffuse water, Beer from Carl Ruben, and experimental part is with particularly with Daigo Hirai, Felix, Yeonjun, and Jean-Louis. And today there are many talks about 5D1 double perovskites, and I wouldn't talk in detail, but the important thing for me is that there are such transitions. After lowering temperature, we obtain quadrupole transition, and then magnetic transition. And here, by X-ray scattering and RIXS, and also ultrasound measurements, there are, people think there are some deformations like here. And in another 5D1 compound, cesium tantalum 2 chlorine 6, again, people observe some structural deformation, and they may be interpreted as based on quadrupolar ordering. And at low temperature, they obtain antiferromagnetic phase. And to describe them, the first starting point would be based on this electronic structure with J effective 3/2 ground state. And but in the previous reports, at least, not all features have been described based on the pure electronic model. And the breakdown of such a thing will happen because apparently we obtain such a deformation, meaning there is electron-phonon coupling. And so we expect there are some electron-phonon coupling, and we may expect there is some Yantera deformation. But I would say in this series of compounds, this deformation is not simple classical Yantera deformation, but we have to fully consider quantum effect, or that is called dynamic Yantera effect. So today's talk consists of there are two parts. First part is based on recent RIXS spectra. I will explain why we have to consider dynamic Yantera effect. And the second part, I will explain what is the benefit considering the work. What happens with dynamic Yantera effect in the ordered pages. So this is the experimental, the experimental data of barium 2 magnesium rhenium O6, and this spectra, in particular, this part shows the excitations from the ground state to the excited state. The important thing is here, the spectra is not symmetric, but asymmetric. And this asymmetry doesn't change even below, below and above the quadrupolar transitions. The shape doesn't change much, so this means we cannot assume structural deformation below the quadrupolar temperature. For example, so if we assume static Yantera deformation below quadrupolar transition, and we expect such a deformation, and of course, if system is somewhere here, and we observe transitions, and under this condition situation, we can see such a symmetric peak like conventional Planck-Condon scenario. But if this is true, then above the quadrupolar transition, Yantera distortion should disappear, and we should obtain symmetric peak. But the experimental data shows this remains asymmetric even above the quadrupolar transition. So we need some scenario, some mechanism that is not simple static Antler effect. And I would say dynamic Antler effect is important. So now I will explain what is dynamic Antler effect. In a word, this is simply a free quantum mechanical treatment of dynamically Antler system. Well, this is a model Hamiltonian. Of each octahedron, we have spin-orbit coupling, and we have electron-phonon coupling, and we also consider nuclear kinetic energy, meaning we treat quantum deformations quantum mechanically. And well, by cartoon, I will explain below. So under this electron-phonon coupling with spin-orbit coupling, we obtain the potential surface right here, and there are three equivalent minima with equivalent tetragonal compression. And now, what quantum effect means? The quantum effect of kinetic energy allows the system to come here, come here, come here. I mean, there is a tunneling, quantum tunneling between different states. And finally, we obtain low energy spectra like this. I mean, linear combinations of different orbital lattice configurations. And so, based on it, we call this is spin orbital lattice entangled state. And of course, this is a simplified picture. And if we numerically diagonalize this Hamiltonian with respect to the magnitude of electron-phonon coupling, we obtain energy spectra shown here. And without electron-phonon coupling, we simply obtain equally separated harmonic levels. But increasing the electron-phonon coupling, the energy spectra changes drastically. Distribution of the energy level changes drastically. So, and the system becomes more stabilized compared with by the tunneling or tunneling effect, and it is shown here. So, well, when dynamic Antler effect happens, we have to consider such a state. And now, on top of it, we simulated L3 RIXS spectra. This is a spectra without electron-phonon coupling. G equals 0 is a spectra without electron-phonon coupling, and I obtain symmetric peak. But increasing the electron-phonon coupling, the peak becomes asymmetric. And this asymmetry is in line with the experimental data at J effective 1/2 peak. And yeah. Yeah, and we also simulated at low temperature and also at high temperature, actually 300 Kelvin. And well, the shape spectra shift a little bit at high temperature, but anyway, in both cases, the this peak is asymmetric. So based on dynamic Antler effect, we can explain this spectrum. And now before we observed high energy peak, but we can observe low energy peak by using other probe. Now we move to oxygen KH RIXS, and this is a simulated data. And without electron-phonon coupling, well, I didn't put elastic peak. And without electron-phonon coupling, we obtain only one peak here. But increasing the electron-phonon coupling, this peak becomes lower and this peak becomes higher. And this peak corresponds to the transitions from the ground vibronic state to some excited states. And such a peak appears in the experiment of one rhenium compound. And this peak can be explained based on the transition here. It means between vibronic states. So based on this, we would say we can, also, sorry, this peak, experimental peak, doesn't change with respect to temperature. And this is again supporting the mechanism of dynamic entry effect. Oh, and such a feature appears in many compounds like osmium compounds and also magnesium rhenium compounds. Well, this is above the transition temperature, but we obtain such a, this group, Stefano obtained such a peak. And this is a experiment by Ibiza, and here they can see some peak, similar peak, and also they show L3 edge doesn't change with respect to temperature. So, yeah. Now, RIXS spectra shows in the family of 5D compounds, there must be dynamic entry effect. And then now we want to consider what will happen, what is the effect of the dynamic entry effect on the ordered phases. And to this end, we developed a theory. And now on each side, we have dynamic entry effect. And to describe the physical quantity, we project every operator on site into low-lying vibronic state. And we describe orbital angular momentum and coordinates in terms of quadrupole operator. And then we consider next nearest neighbor super exchange interaction and elastic interaction between low-lying vibronic states. And this is our model Hamiltonian. And then we calculated 0 Kelvin mean field phase diagram. This is the magnitude of elastic coupling, and this is the type of elastic coupling. And without elastic coupling, we obtain so-called FM110 or canted AFM phase. And turning on the elastic coupling, we obtain, in some place, we obtain ferromagnetic phase, and in some place, we obtain antiferromagnetic ferro-quadrupolar phase. By using them, we can explain a couple of experimental data. First one is about magnesium rhenium oxide. The important thing is here, this is some specific heat and so on. And yeah, important thing is here. Within the previous pure electronic model, people couldn't explain this part, but now we explain the development of this deformation here. And yeah. And in the case of tantalum compound, this type of phase hasn't been explained within the previous theory, but now we could explain this feature. So based on a single viewpoint, we could explain both rhenium compounds and also tantalum compounds. And finally, I will discuss a little bit about the effect of ordering on the RIXS spectra again. In the previous discussion, I simply consider isolated octahedron, but in reality, there is an ordering at low temperature. And to consider the effect, I imposed some effective field and then simulated the low energy spectra. 0 is the ground state, and this red dashed line shows the evolution of the low energy spectra. And with the external field, they split and changes a lot. And this blue line or green dashed line indicates the classical limit. And the calculated spectra reaches classical limit when external field is like 0.1 electron volt. But from the experimental data, we can estimate magnitude of external field should be like 0.01 electron volt, 10 times smaller. And what happens if vibronic state doesn't change much? And as a consequence, we with or without vibronic state, vibronic ordering, the spectra doesn't change the shape much. So, yeah. And this black line, gray dash, this is mistake, but this gray dash line shows the spectra above the transition temperature, and black line shows the spectra below the transition temperature, and they don't change much. So, conclusion, today I talk about RIXS of 5D1 double perovskites and say this spectra shows dynamic antenna effect is universal feature of the family of cubic 5D1 double perovskites. And the second part is vibronic orders. By considering the ordering of the vibronic states, we could explain all the main features of the ordered phases of the 5D1 double perovskite. Thank you very much.